I'm Soyeon Lee, the author of Odpg Outfitting Diffusion with Post-Guided Conditions. I'm very honored to give a presentation. I've co-worked with Jintae Park and Sanghyuk Park. Let me start the presentation. Virtual try-on technology enables users to see how clothes will look on them without physically trying them on using advanced image synthesis techniques. Although the virtual try-on technology has struggled with a natural image synthesis limiting its industrial adoption, the rise of diffusion models has resolved many of these issues, enabling high-quality, realistic image generation. As a result, virtual try-on is now gaining significant attention for its potential in fashion and other applications. Nevertheless, existing virtual try-on methods still face certain limitations. They often rely on explicit garment masking, which leads to the loss or distortion of semantic information, and requires additional segmentation and detection models. This approach stems from the lack of paired datasets, where images of the same person wearing different garments are unavailable. While explicit masking addresses this issue, it increases complexity and compromises quality. In diffusion models, managing multiple conditions like changing both pose and garment adds another challenge. The model must focus on relevant regions, for example, like altering pose without affecting the garment, but it often struggles to do so effectively. To mitigate this, existing methods commonly adopt a two-stage process, first adjusting the pose and then applying the garment, or vice versa. While this simplifies learning, it introduces inefficiencies and limits the model's coherence. To address this issue, we propose Odpg, a novel approach to virtual try-on. Odpg enables controllable multi-condition generation. Unlike traditional methods, it eliminates the need for explicit garment warping by integrating garment information implicitly during the generation process. Additionally, our bias-augmented query attention mechanism captures complex relationships between appearance, pose, and garment, reducing dependency on fully paired datasets. Finally, Odpg unifies pose transfer and garment synthesis in a single end-to-end process, simplifying the pipeline while maintaining high-quality results. This is the overall pipeline of our model. The source image features are extracted at 3 different scales using a swing transformer. Similarly, the garment image passes through a swing transformer with features extracted at 4 scales. And the 4th scale feature is passed through a transformer decoder with learnable queries which outputs a general garment information to condition the diffusion unit structure at each downsample and upsample block. Multi-scale features from both the source and garment images are combined via bias-augmented query attention mechanisms, with fine details added as conditions in the upsampling blocks. Additionally, pose information processed through a ResNet provides course guidance during the downsampling blocks, where both garment and pose are conditioned together. This is followed by the intuition that garments should be dressed onto the skeleton from its foundation, creating a structural base. In contrast, finer details like appearance are conditioned during the upsampling blocks, giving the impression of painting the appearance onto the preformed structure. Now, let me elaborate our bias-augmented query attention. Our unit-based diffusion model incorporates a learnable query vector which interacts with garment, pose, and appearance features via a cross-attention mechanism during the denoising process. This query learns to extract natural garment features that align with the source human and the target pose. To initiate the process, we first flatten the coarsest garment feature map and pass it through a transformer decoder. And this generates a refined garment feature map, FG out, capturing general garment information. Using learnable projection metrics, WKL and WVL, we compute the keys and values from FG out. These keys and values are used across the denoising blocks to extract garment features specific to the target pose. And this step creates a structural base where pose and garment information are integrated. In the upsampling blocks, we incorporate both garment and appearance information using the appearance encoder, which captures fine-grained texture details. At each scale, the encoder computes bias based on garment and appearance features, which are added to learnable queries. This process refines the garment features with detailed textures, ensuring the final image accurately reflects the source appearance, target garment, and target pose. The overall attention mechanism is summarized as follows, where the attention output FOL is added to the noisy latent at each step, guiding the denoising process. To optimize the training process, we use a self-reconstruction mechanism where the source image reconstructs itself. The total loss function combines the reconstruction loss with the standard MSE loss. And to further enhance the training process, we adopt a cumulative classifier-free guidance mechanism to strengthen the integration of source appearance, target pose, and garment features. Inspired by instruct pix to pix, we randomly drop some of these multi-conditional inputs, pose, appearance, or garment, during training. This allows the model to flexibly handle conditional or unconditional denoising, providing better control over the output. The modified classifier-free guidance is expressed as follows. We conducted experiments on the dip fashion and fashion try-on datasets. Also, using OpenPose, we extracted joint key points and trained our architecture on both datasets. Here are our qualitative results. The generated images in the output column of both tables demonstrate that our end-to-end architecture effectively integrates garment and pose information to produce multiple dynamic virtual try-on results. We evaluated our model using FID, SSIM, and LPIPs, which measure overall quality, structural similarity, and perceptual diversity of the generated images. Since our model adopts an end-to-end multi-conditioning approach that simultaneously modifies both pose and garment, there is an inherent trade-off in metrics compared to models that focus solely on garment manipulation or use multi-stage processes. These models are garment-only conditioning models. These models excel in SSIM and LPIPs by focusing exclusively on garment conditioning. Despite handling the more complex task of simultaneous pose and garment changes, our model achieved competitive SIM and LPIP scores while delivering reasonable performance in these metrics. And these are multi-stage models which rely on separate steps for pose transfer, garment alignment, and refinement, often achieving strong metrics by specializing in these stages. In contrast, our end-to-end approach simplifies the pipeline, avoiding the need for multiple training stages. Notably, Odpg outperforms all other models in FID, indicating that our generated images are closer to real images in overall quality and distribution. We compare our Odpg model with existing methods like image dressing, IDM Vition, and OOTD diffusion. These models often rely on masking the person and fitting the garment onto the existing silhouette, leading to issues like oversized or distorted garments when dealing with thick or layered clothing. For example, in the second row, Remnants of a hood may appear when dressing someone in non-hooded garments. In contrast, our Odpg model ensures garments fit naturally to the body structure regardless of the original clothing. This strengthens highlights Odpg's ability to produce realistic and well-integrated results, addressing the common limitations of existing models. To demonstrate the effectiveness of our method, we conducted experiments by varying the input biases to the appearance encoder. Specifically, we tested 5 cases. In the appearance-only case, the source appearance details are captured well, but garment features are not fully represented. Doubling the appearance bias improves the preservation of finer details such as shoe color, but garment representation remains limited. Conversely, in the garment-only case, the target garment is accurately reflected, but other features like the original pants color are lost. Doubling the garment bias enhances garment representation, but causes the loss of non-garment features such as hairstyle. By combining both appearance and garment biases, we achieve a balanced outcome that preserves critical non-garment features while accurately reflecting the target garments. This experiment demonstrates that our method can effectively control the latent space, balancing the representation of garments and appearance features to produce realistic and visually consistent virtual try-on results. We compared the effect of applying explicit gray masking to the upper body region of source images with using our method without masking. While our training setup involves the source person wearing the target garment, which may appear to limit generalization to unseen garments, our results prove otherwise. The model doesn't simply replicate the input, it learns what and where to modify effectively. For garments like complex textures or patterns, explicit masking often simplifies designs, reducing details like the number of stripes or pattern intricacy. In contrast, our non-explicit masking method produces better results. Explicit masking tends to dominate appearance information, leading the model to extract irrelevant or misleading features. This disrupts the denoising process, causing distortion in colors and patterns. Additionally, the similarity between the gray mask and the background further confuses the model. To sum up, in this work, we introduce outfitting diffusion with pose-guided conditioning, a novel virtual try-on framework that implicitly integrates garment, pose, and appearance features into a diffusion-based unit architecture. Using a bias-augmented learnable query mechanism, our model generates realistic try-on images without explicit garment warping, capturing fine-grained details like textures, fits, and natural pose alignment. Unlike traditional multi-stage pipelines, Odpg provides an efficient end-to-end solution that simplifies the process while maintaining high visual quality. Our experimental results demonstrate the model's ability to generalize beyond fully paired datasets, reducing data dependency and achieving impressive results in realistic try-on synthesis. Looking forward, we see exciting directions for future research. One key area is extending the model to handle video inputs, enabling dynamic garment and pose transitions for interactive video-based try-on scenarios. Additionally, the implicit learning strategy in Odpg could be adapted to other domains facing data limitations, offering broader applications in fields where paired data sets are scarce. These future directions highlight the versatility and potential of Odpg for advancing virtual try-on technology and addressing challenges in other data-driven tasks. Thank you for your attention.